Hello guys, welcome aboard Apex Math. My name is Bino. In this video, we go through question 1 from the 3rd of August 2025 N5 Power Machines question paper. Question 1, which is on adiabatic compression, states that a certain gas occupies a volume of 0,453 meters, but I believe that was supposed to be meter cube, at 170 kilopascals and a temperature of 21 degrees Celsius, and is adiabatically compressed to 1380 kilopascals. The density of the gas at standard temperature and pressure is 1,362 kilogram per meter cube, and CV, which is the specific heat capacity under constant volume, is equal 716 joules per kilogram kelvins. Before we can answer question 1.1, we start by extracting our data, and we start by extracting the data for the initial condition before the adiabatic compression. Adiabatic compression simply means the gas is being compressed without any heat entering or leaving the system. All the temperature changes occurs only from the work done on the gas. So we start with the initial condition, and the statement read that a certain gas occupies a volume of 0,453 meter cube at 170 kilopascals and a temperature of 21 degrees Celsius. That is the initial condition of the gas, where the volume is equal, so the volume 1 is equal 0,453 meter cube, and the pressure number 1 will be equal the 170 kilopascals, and the temperature number 1 is equal 21 degrees Celsius. So we have T1 is equal 21 degrees Celsius, but then we have to convert it to kelvins by adding 273. So this will be equal 294 kelvins, and this gas will be adiabatically compressed. For now, it's occupying a volume of 0,453 meter cube at 170 kilopascals and a temperature of 21 degrees, and it's now adiabatically compressed. And when we adiabatically compress it, there is no heat transferred to the system. So there is no heat which is transferred to the system or transferred out of the system. But that does not necessarily mean that the temperature is not going to increase. The temperature is going to increase because of the work done by compressing the gas. Remember that work done is the force multiplied by the distance it acts over. So during adiabatic compression, all the temperature increase comes from this work being done on the gas. When we apply a force on the piston, it moves the piston down by a distance. So we do work on the gas, and that work increases the gas internal energy, causing its temperature to increase. So the gas will occupy the lower part of the vessel. So after our adiabatic compression, we have our final condition, and we have to extract our data for the final condition. After the adiabatic compression, we'll have volume number 2, and also have pressure number 2, and also have temperature number 2. From the above statement, we were told that the gas is adiabatically compressed to 1380 kilopascals. So we have 1380 kilopascals as our pressure number 2. After the adiabatic compression, we were given only the pressure, so no volume and temperature, so we can have X and Y in the meantime. So we have another condition. The STP condition. The STP condition exists outside of the adiabatic process. The adiabatic process is what happens to a gas, and the STP is an environment like a hospital of gases where we determine their true identity. So at STP, the density of this gas is 1,362 kilogram per meter cube at that STP. So we have the standard temperature and pressure condition, commonly known as the STP. So it's a condition. At this STP, we were given the density of this particular gas, and the temperature is always constant for all the gases, and it's 273 kelvins, and I believe it's available in the formula sheet. And the pressure is always 101,325 kilopascals, and it's also available in the formula sheet. And the density was given as equal 1,362 kilogram per meter cube. So for density, we have 1,362 kilogram per meter cube. So we have extracted all the data for the initial condition, the final condition, and the standard condition. So now, question 1.1, we have to calculate the value of the gas constant. So we determine the R, the gas constant, and we determine it from this formula. PV is equal mRT, where the R is the gas constant. So let's see, from the initial condition, we have volume number 1, pressure number 1, and temperature number 1. So from our formula, we have that volume, that pressure, and the temperature, but we don't have the mass and the gas constant. So we can use the initial condition. How about we try the final condition? But on the final condition, we are only given the pressure number 2. So the standard temperature and pressure condition. So from the standard temperature and pressure condition, we have that temperature, we have that pressure, but we don't have the volume and the mass, but we are given the density, and the density relates mass with the volume. So with the density is mass divided by volume, making the mass the subject of the formula. We have mass is equal density multiplied by volume. So let's substitute the mass. So you have PV is equal the mass. In the place of the mass, we have the density multiplied by the volume. Density multiplied by volume. Now we have the R, we multiplied with the temperature. So from here, we can see that we have V and V there. So the V's will easily cancel out. So we divide both sides of the equation by the V so that we can cancel out the V's. So we'll be left with P, which will be equal density multiplied by the gas constant R multiplied by the temperature. But we have to make that R the subject by dividing both sides of the equation by the density multiplied by temperature. And now the pressure divided by the density multiplied by the temperature will be equal the gas constant R. From here, it's just a matter of substitution. So the pressure is always 101,325 at standard temperature and pressure. So I expect you guys to memorize this pressure, and the density was given as equal 1,362. We have 1,362, and the temperature at standard temperature and pressure is 273 kelvins. So our R will be equal 0,273 kilojoules per kilogram kelvins. And this will be our answer for question 1.1. Question 1.2, we have to determine the value of the CP, that is the specific heat capacity under constant pressure. From question 1.1, we determine that our R is equal 0,273 kilojoules per kg kelvins. Now we use the formula R is equal Cp minus the Cv. We make the Cp, the specific heat capacity under constant pressure, the subject. So we have R plus Cv, which will be equal the Cp. We already determined this R, and we are given the specific heat capacity under constant volume, the Cv, as 716 joules per kg kelvins. So the Cv is given as equal 716 joules per kilogram kelvins. And now Cp will be equal the R plus the Cv, but then we have a discrepancy. The R is in kilojoules and the Cv is in joules. So we can divide the Cv by 1000 so that we can convert it to kilojoules. So you have 716 divided by 1000, and this will be equal 0,716 kilojoules per kilogram kelvins. So now our R, we substitute 0,273, and our Cv, we substitute the 0,716 kilojoules per kilogram kelvins. Our Cp now is equal 0,989, and this is in kilojoules per kilogram kelvins, and this will be our answer. Question 1.3, we have to calculate the value of gamma to 2 decimals, and gamma determines how hot a gas gets when you compress it adiabatically, and it can only be between 1 and 2. So there is no gamma which is less than 1 or more than 2. It's always between 1 and 2. And a higher gamma indicates that when you compress the gas, it gets hotter easily. And a lower gamma around 1.2, 1.3 indicates that the gas heats up less when compressed adiabatically. So a higher gamma indicates that the gas gets hotter faster when compressed, and a lower gamma indicates that the gas gets hotter slowly when compressed. The formula to calculate gamma, we have gamma is equal Cp, the specific heat capacity under constant pressure, divided by Cv, the specific heat capacity under constant volume. We copy and paste. So our gamma will be equal, our Cp is equal 0,989, and our Cv is equal that 0,716. So we substitute 0,716 in the place of the Cv, and this will be equal 1,3812, but then they said 2 decimal places, so we'll have 1,38, and it doesn't have any SI unit because the SI unit from the Cp and the SI unit from the Cv are the same, so they will just cancel out each other, and this will be our answer. Question 1.4, we calculate the final absolute temperature, that is temperature number 2, temperature after the final condition. So let's get rid of this STP condition. We are at question 1.4, and the formula that we use, we have temperature number 2 divided by temperature number 1 is equal raised to the power gamma minus 1 divided by gamma. So we make the T2 the subject of the formula by multiplying both sides of the equation by that T1. So we have T1 on the left and also multiply by the T2 on the right, such that T2 will be equal the pressure 2 divided by pressure number 1, all raised to the power gamma minus 1 divided by gamma multiplied by T1. Now we can substitute. So we have temperature number 2 is equal the pressure number 2, which was equal, I believe it was 1380 kilopascals. Yes, that 1380 kilopascals is our pressure number 2. So here we have 1380 divided by pressure number 1, which is equal 170 kilopascals. So you have that 170 kilopascals raised to the power gamma, which was 1,38 minus 1 divided by 1,38 multiplied by the temperature 1, which was, so it was 21 degrees Celsius. We converted it into 294 kelvins. So we have 294 kelvins, and the temperature number 2 will be equal 523,323 kelvins, and this will be our answer. Question 1.5, we have to calculate the change of internal energy, and it's denoted by delta U. So this is our unknown, and from this formula we have PV is equal mass multiplied by the gas constant R multiplied by the temperature T, and we had initial condition. From the initial condition, we moved to the final condition. And from the left hand side of the formula, we have that PV. So from the initial condition, we are going to have P1 V1 from the left hand side of the formula, and from the final condition, we are going to have P2 V2. And from the right hand side of that formula, the MRT, the mass and the gas constant are constant. So we have M multiplied by R multiplied by temperature number 1. And on the final condition, we have M multiplied by R multiplied by temperature number 2. So we have what we call the change in PV, which will be equal the pressure number 2 multiplied by volume number 2 minus the pressure number 1 multiplied by volume number 1, which is equal, this is still the same as the mass multiplied by the gas constant multiplied by the temperature 2 minus the mass multiplied by the gas constant multiplied by temperature number 1. But from here, we can take that MR, since they're the same, we can take that MR as our common factor, such that MR will be multiplied with the temperature number 2 minus temperature number 1. So why do we have all this? So the change in internal energy is equal the change in the PV divided by the gamma minus 1. So it's either we use the P2 V2 minus P1 V1. So P2 V2 minus P1 V1 divided by gamma minus 1, or to determine the change in internal energy, we can use the M multiplied by R into T2 minus T1, which will also be divided by the gamma minus 1. And this will be equal, so it's either we go with P2 V2 minus P1 V1 or MR into T2 minus T1. So let's go with the MR, where we substitute our mass for X, and our R is 0,273 from 1.1, and our temperature number 2 was equal 523,323. So we have 523,323 for temperature number 2 minus temperature number 1, which was equal 294 kelvins. So in the place of the T1, we substitute 294, and the gamma, we determine the gamma as equal 1,38 minus 1. So we have to determine the X, and we are going to use the formula PV is equal to MRT. And we are going to use the initial condition, since we have the volume number 1, we have pressure 1, and the temperature 1, and the gas constant. So the only missing quantity is the mass. So in the place of the P, we substitute, so this is P1 V1 and T1. We substitute 117 in the place of P1, and in V1 we substitute 0,453. We have to determine the mass, and the gas constant was equal 0,273 from question 1.1, and temperature 1 is equal 294 kelvins. So now let's divide both sides of the equation by 0,273 multiplied by 294, so that we can make that M the subject. And our mass M will be equal 0,959 kilograms. We can now remove that X, and we make some space for the 0,959 I mean. So you have 0,959 kilograms, and the change in internal energy, delta U, will be equal 158,075 kilojoules. Thank you guys for watching. If you have any questions, you can drop them in the comment section below. Remember to subscribe, like, and share this channel if you want to see more of Power Machines videos.